Today, we're stepping into the ultimate time machine, not just thousands or millions of years ahead, but an unimaginable 10 quintillion years into the future. A future where our universe is no longer recognizable. Stars have burned out, galaxies have collided, and black holes dominate the cosmic stage. Earth? It's nothing more than a forgotten ember, drifting in silence. But before we take that colossal leap, let's ground ourselves. What does 10 quintillion years even mean? Imagine the number 1 followed by 19 zeros. 10 billion billions. A number so vast we can't even fully process it. Your screen couldn't contain all the zeros. And yet, this is the time scale written into the destiny of the universe. But let's not jump too far ahead. Our journey begins in the relatively near future, a mere 1 billion years from now. And trust me, what awaits is nothing short of terrifying. Picture Earth as you know it, oceans glistening blue, forests breathing with life, clouds drifting across a vibrant sky. Now strip all of that away. In just 1 billion years, this jewel of the cosmos is reduced to a parched, lifeless husk. Our once blue marble will be a scorched brown rock. Why? The culprit is our own sun. You see, the sun isn't stable. For every 100 million years, it grows hotter by about 1%. Today, that might sound trivial, but stretched across geological time, it's catastrophic. In 1 billion years, that small but relentless increase will drive Earth's surface temperature to around 47 degrees centigrade or 117 Fahrenheit. A world where heat itself becomes lethal. The chain reaction begins quietly. The carbon cycle collapses. Plants, unable to photosynthesize in the blistering heat, vanish. Without plants, oxygen dwindles, and the animals depending on them follow. Life retreats to the oceans. But even there, survival is temporary. As the sun continues its march toward greater heat, Earth's oceans boil away into the sky, leaving nothing but salt plains and barren deserts. Our beautiful world, once filled with song, movement, and endless diversity, it becomes a graveyard of rock and dust. And what about us, humans? Well, if we survive to see that far into the future, it won't be here. Mars won't save us either. Its thin atmosphere and proximity to the sun would make it just as doomed. To endure, humanity would have to look far beyond establishing colonies among the outer planets and their moons, or perhaps even migrating to entirely new star systems within the Milky Way. By then, Mars as a settlement would be a distant memory, little more than a footnote in human history. Instead, we might carve out civilizations on Europa, Titan, or even drifting stations orbiting brown dwarfs, planets and moons shielded from the sun's fury. But there's another possibility, a radical one. Perhaps a branch of humanity will escape biology altogether, uploading consciousness into machines, living as digital minds across the cosmos. These virtual humans could, in theory, last forever. Yet even they cannot exist without energy. Their servers, processors, and synthetic worlds would require massive amounts of power. That means physical humans, or whatever we evolve into, must still colonize and manage real worlds to keep our digital offspring alive. Living forever in a virtual utopia sounds extraordinary. But here's the catch. None of it is possible without solving energy. Even today, we struggle to power our world sustainably. Imagine the challenge of fueling interstellar civilizations or immortal digital beings. Without breakthrough energy technologies, Fusion, antimatter harvesting, or even tapping black holes themselves, these visions remain dreams. So let's climb back into our time machine and push forward again. Not just 1 billion years, but 10 billion years ahead. The solar system is unrecognizable. Our sun, once blazing yellow in the sky, has shrunken down to the size of Earth. It glows faint and white, a white dwarf, the final stage of a medium star's life. What happened in the intervening time is violent, almost apocalyptic. Roughly 5 billion years from now, the sun will swell into a red giant, its surface expanding past Mercury and likely engulfing Venus. Earth will not escape either. Whether it's swallowed whole or stripped down to a bare iron core, our planet will be annihilated in the process. When the sun finally sheds its outer layers, it will collapse into a white-hot cinder. The white dwarf you now see glowing dimly in the cosmic dark. Over trillions of years, even that ember will cool into a black dwarf, a frozen star remnant. But while our sun was dying, something even more spectacular was unfolding on a cosmic scale. The Milky Way galaxy, our galactic home, collided with its massive neighbor Andromeda. The two were always destined to meet. Pulled by gravity, Andromeda raced toward us at nearly 400,000 kilometers per hour, 250,000 miles per hour. When they finally merged, the night sky would have been a breathtaking and terrifying sight. Imagine looking up to see entire star systems, flung like sparks across the heavens. To an observer caught within, it would feel like being inside a giant snow globe. Only instead of snow, it's stars, planets, and worlds being scattered. The cosmic dance lasted millions of years, eventually forging a new elliptical supergalaxy, often nicknamed Milkomeda. And this is only the beginning of the universe's transformation. When the Milky Way and Andromeda finally collided, the result was something new. A titanic, merged supergalaxy called Milkomeda. It stretched across the heavens like a colossal swirl of light, billions of stars thrown into new orbits, nebulae shredded and reborn, entire solar systems cast adrift. But here's the question. In a collision of this magnitude, would stars actually crash into each other? Your instinct says yes. Billions of stars smashing together in a cosmic demolition derby. But reality is stranger. Stars are separated by hundreds of billions of kilometers, so much empty space that the odds of two stars colliding are vanishingly small. Imagine 2 grains of sand a football field apart. That's how distant stars truly are. The galaxies blend, but the stars themselves simply weave past each other like dancers in an endless waltz. So what happens to our own solar system during this grand merger? Simulations give us an unsettling answer. There's roughly a 50% chance that our solar system will be flung 3 times farther from the galactic core than where it sits today. And there's a 12% chance it will be hurled completely out of Milkomeda, ejected into the cold darkness between galaxies, a rogue solar system adrift in the void. But by that time, humanity will no longer call the solar system home. If our species survives across billions of years, we'll have long since abandoned this fragile cradle. Colonies will stretch across star systems far removed from this cosmic collision, chosen precisely because they are stable, safe, and free of galactic upheaval. For us, the Milky Way, and later Milkomeda, will be nothing more than a chapter in our origin story. Say farewell to the galaxy we once knew. Now let's push the dial forward again. 22 billion years into the future. The universe faces something far more sinister than galaxy mergers. Physicists call it the Big Rip. The Big Rip is not science fiction. It's a real theoretical possibility based on what we know about dark energy. Dark energy is the mysterious force that drives the universe's accelerating expansion. Even today, it's pulling galaxies farther and farther apart, faster and faster. Scientists don't fully understand what it is. It's invisible, untouchable, and makes up about 70% of the universe. But if its power grows unchecked, the future becomes terrifying. In around 20 to 22 billion years, the acceleration could become so extreme that gravity itself can't hold things together. First, galaxy clusters would unravel, their members drifting, apart like leaves on a storm. Then galaxies themselves would shred, stars pulled away from one another. Solar systems would disintegrate, planets torn from their stars. And in the final seconds, even atoms would be ripped apart, protons, neutrons, and electrons scattered into nothingness. This is the Big Rip, the universe literally tearing itself apart at every level. Evidence suggests dark energy is real, but whether it will cause a big rip is still uncertain. So let's assume for now that the cosmos escapes this fate. The universe continues on, but that doesn't mean it's safe. Let's journey ahead through the next 100 trillion years. This era is called the Stelliferous Era, the Age of Stars. It began about 150 million years after the Big Bang, when gravity first coaxed hydrogen gas into collapsing clouds that ignited the very first stars. Since then, new stars have continually been born in nebulae, massive clouds of hydrogen and dust glowing like cosmic nurseries. But stars are not eternal. They live and die by rules written in their mass. The heavier the star, the shorter its life. The smaller the star, the longer it burns. Take a brown dwarf, an object just under 8% the mass of our sun. Too small to ignite true hydrogen fusion, it's a failed star. Brown dwarfs smolder dimly, glowing only from leftover heat. Over eons they fade, cooling until they are invisible embers adrift in space. Now compare that to a giant star 10 times the mass of the sun. It burns furiously, its core a raging furnace, devouring fuel at a breakneck pace. In just 20 million years, a cosmic heartbeat, it burns out and dies, exploding in a violent supernova. From its ashes, one of two monsters is born, either a neutron star so dense that a teaspoon of its matter outweighs a mountain, or a black hole, a gravitational abyss from which not even light can escape. Our own sun sits between these extremes. Its lifespan is roughly 10 billion years, halfway gone already. When its time comes, it will swell into a red giant before shrinking into a white dwarf, leaving behind only its glowing corpse. But the majority of stars in the universe are red dwarfs, smaller than the sun, between 8% and 50% of its mass. They burn cooler, dimmer, and far longer. Some may live for 80 to 100 billion years before finally fading. During this stelliferous era, these red dwarfs will be the last stars shining across the cosmos, and so as trillions of years pass, one by one, the stars die out. The universe gradually darkens. The sky that once glittered with endless light becomes sparse, then empty. Nebulae are used up. Star formation ceases. Brown dwarfs cool to black. Neutron stars fade. White dwarfs dim. What remains are only the remnants of a brilliant age, corpses of stars, frozen embers, and black holes silently prowling the void. This is the end of the stelliferous era, the twilight of stars. You've already witnessed stars bursting into life and fading into death, galaxies colliding in slow-motion dances, and planets rising and falling into oblivion. But there's a quieter, equally important story unfolding beneath all of this chaos. Every time a star dies, it doesn't just vanish. It leaves something behind. When a star ends its life, it expels elements forged in its core. Carbon, oxygen, iron, even the gold in your jewelry, hurling them out into the void. These elements seed the birth of new stars, planets, and eventually life itself. This cycle has powered the universe for billions of years. But there's a problem. Not all of a dying star's mass is recycled. With every generation, a portion of matter becomes locked inside stellar remnants, white dwarfs, neutron stars, black holes. And as eons pass, the supply of raw hydrogen dwindles. The cosmic factories of creation begin to close. Eventually, the universe simply runs out of fuel. No more hydrogen gas, no more new stars. The stelliferous era, the brilliant age of starlight, comes to an end. Welcome to your next stop, the degenerate era. And no, not the internet kind of degenerate. This is something far more somber. As you drift through space in this age, the universe feels profoundly different. The once vivid heavens, spangled with billions of suns, are now a cosmic graveyard. The only objects left are stellar corpses, white dwarfs glowing faintly, brown dwarfs cooling in silence, neutron stars spinning like cosmic lighthouses, and black holes swallowing whatever drifts too near. The night sky is no longer alive with light. Instead, it is haunted by shadows. And what about us, humanity? Even if we spread across galaxies, we would still need stars to orbit, planets to inhabit, and energy to survive. But in this age, such luxuries are rare. One possibility is that humanity abandons physical form altogether, existing purely as patterns of energy or information. A kind of post-biological immortality. It sounds dazzling. Beings of pure energy drifting through the void. But there's another possibility hinted at in the deepest corners of physics. The birth of a new universe. Some scientists speculate that quantum fluctuations or collapsing black holes could seed entirely new realities, universes branching like leaves from a tree. Perhaps long after the degenerate era has darkened this cosmos, our descendants might step through into another. Still, even in this dark age, occasional fireworks light up the void. When two brown dwarfs collide, their combined mass could ignite, fusion, sparking a new star that burns for trillions of years. When two white dwarfs slam together, they can explode in a dazzling supernova, briefly illuminating the cold dark with a final burst of brilliance. But these events are rare. For the most part, the universe is growing colder, quieter, lonelier. And then comes the slow unraveling of matter itself. Over mind-bending stretches of time, 10 decillion years into the future, that's a 1 followed. By 34 zeros, even the most stubborn stellar remnants begin to fade. White dwarfs, brown dwarfs, neutron stars, all decay as the fundamental particles inside them begin to break down. This process is called proton decay. In our current physics, protons, the tiny particles at the heart of every atom, appear stable. But some theories predict they aren't eternal. Given enough time, they disintegrate. A white dwarf in this era won't shine like a star anymore. Instead, it will glow faintly, dimmer than a light bulb, gradually flickering out as its protons unravel into nothingness. It's almost poetic, the death of matter itself, the building blocks of reality dissolving, molecule by molecule. Fast forward again. You're now at 10 duodecillion years into the future, a 1 with 40 zeros after it. By this time, the degenerate era is ending. The last remnants of normal matter are gone. Planets, stars, dwarfs, all erased from existence. The universe is colder than absolute desolation. But one type of monster still roams the dark: black holes. They dominate this epoch so completely that scientists call it the black hole era. These titans of gravity feed relentlessly, swallowing stray gas, rogue planets, even entire star remnants. Not even light escapes their grasp. Imagine the universe reduced to a few glowing embers, and in the background, vast black holes lurking like silent predators. They are cosmic zombies, feeding endlessly, growing denser, hungrier, more massive with every morsel they consume. Compared to them, even the most terrifying villains humanity ever imagined, Thanos, Galactus, demons from our myths, seem like shadows of shadows. And yet, as unstoppable as they appear, even black holes will one day meet their end. Did I mention that nothing escapes a black hole? Yes, nothing can outrun its pull. Not matter, not light, not even the desperate scream of a collapsing star. But there is one tiny exception: a whisper at the edge of eternity. Stephen Hawking, one of the greatest minds of our age, proposed that black holes aren't completely eternal. They leak. This strange phenomenon is called Hawking radiation. Here's how it works. Space isn't empty. Even in the deepest void, particles constantly flicker in and out of existence. Tiny twins appearing together, then instantly annihilating one another. But near the event horizon of a black hole, something extraordinary happens. One twin falls inward, vanishing forever. The other escapes, stolen from the darkness. To us, that escaping twin appears as radiation. Over trillions, quadrillions, and eventually Google years, this steady trickle of Hawking radiation slowly robs black holes of their mass. The monsters of the cosmos, the very engines of destruction, eventually die, fading like candles burning out in the endless night. If you had the patience to ride a time machine long enough, you could watch them disappear one by one. Titans collapsing not in explosions of fire, but in silence, leaving behind only emptiness. Now, you've arrived at the final stop, the edge of time itself. A Google years into the future, a 1 followed by 100 zeros. Try to imagine it. Numbers lose their meaning here. By now, the last black hole has radiated away its final atom of mass. The universe has entered what scientists call the dark era. What remains? Almost nothing. The cosmos is cold, silent, and utterly black. No galaxies, no stars, no planets. Only the faintest scattering of subatomic particles, adrift in a void so stretched that even light years are meaningless. These particles are separated by distances so vast, they might never collide again for the rest of eternity. The universe, once brilliant, fiery, and alive, is now a frozen graveyard. This is the Big Freeze. The temperature hovers just above absolute zero, a place where no process of life, no fusion, no spark can survive. Energy is evenly spread, diluted beyond use, and the relentless force behind it all, dark energy, continues pushing space apart, forever expanding, forever cooling. But what if this isn't the end? Some scientists whisper of another possibility, the Big Crunch. In this vision, expansion eventually halts. Gravity takes over. Galaxies, matter, and even space itself collapse inward, folding the universe into itself. Imagine reality played in reverse. Stars unburning, galaxies unspiraling, time itself rewinding until everything returns to a single searing point. From that point, perhaps, a new Big Bang, a cycle eternal, expansion, collapse, rebirth. Has it happened before? Could we be living in just one loop of an infinite cosmic cycle? We don't know. But current evidence points elsewhere. Dark energy appears too strong, its grip too relentless. The most likely fate is still the Big Freeze, not a rebirth. So what does this mean for us? For the human race? Even before the Dark Era, survival would be nearly impossible. Once star formation ends, once galaxies grow cold, humanity cannot rely on natural suns to build habitable worlds, but human ingenuity may yet write a new chapter. Perhaps our descendants abandon physical form, existing as pure consciousness or energy. Perhaps they escape into artificial universes, pocket realities, engineered in labs by civilizations so advanced they rank as type 6 or 7th on the Kardashev scale. Entire universes as safe havens, built by hand. Consider this. In just 200 years, humanity leapt from the Industrial Revolution to quantum computers, genetic engineering, and artificial intelligence. Imagine what 1,000,000 years of progress could bring. Or 1,000,000,000. Or 1,000,000,000,000. If intelligence endures, if the spark of curiosity, the drive to explore survives, then even as the universe dies, we may carry its story forward. Perhaps to another cosmos, perhaps to an infinite chain of worlds. The end of the universe may not be the end of us. So here you are, at the last breath of creation. You've traveled from the fiery birth of stars to the silence of absolute darkness. From galaxies colliding to black holes evaporating. From the stelliferous era of light through the degenerate era of remnants into the endless night of the Big Freeze. The universe began in fire. It may end in ice, but the story isn't finished, because the greatest question remains: will humanity surrender to the silence, or will we become the architects of eternity? If you've journeyed this far with me, don't stop now. Hit subscribe, tap the like button, and join us as we explore the greatest mysteries of space, time, and the human future. This is more than science. It's our story.